So far, discussing mobility and IP, we always assume that we have at least some infrastructure. So, mobile IP, the agents they need, the fixed network, they're somewhere there. We have DNS and routing and bindings in here and there. But what happens if there's no infrastructure at all? If all the infrastructure is destroyed, remote areas, ad hoc meetings, disaster areas, where you cannot rely on infrastructure, it's too dangerous. Maybe it's too expensive. What do we do then? And we will see the main topic here is routing. It's simple in this example. Well, you simply forward the traffic. But if we do not have default routers, what do we do? All the nodes should be able to forward, or what can we do? And a solution for these questions are the so-called wireless ad hoc networks, a network without infrastructure. You simply use the components of all the participants for the networking. The simple networks are single hop networks. All partners are one hop away, that's simple. That's not interesting. Bluetooth, piconets or whatever. The interesting case is multi-hop networks to cover larger distances, circumvent obstacles. These are, well, we learned a bit about scatternets, tetra, police networks, car networks. But if we work on layer 3, these are the mobile ad hoc networks. IEEE defines some standards for the layer 2, but remember the issues, layer 2 addresses, layer 3 addresses, scalability, so we cannot really scale up layer 2 networks. But on layer 3, it should be possible. If you compare ad hoc networking with mobile IP, you will see both have mobile devices, mobile end systems, but the Manets, they also have mobile routers. This can be co-located in one device or two devices, but mobile routers, that's now the interesting part. Mobile IP, DHCP, all these things, they need a fixed network. So what is the problem number 1 if we look at mobile ad hoc networking? Quite clearly, routing. The problem is ad hoc networks can be very, very dynamic. If we have in addition wireless ad hoc networks, that means the channel quality varies over time. So here you see an example where you have maybe bidirectional connections of quite good quality, unidirectional connections, or bidirectional kind of bit asymmetric connections. So asymmetric connections are possible and they are very, very, very common, as well as unidirectional connections. Plus, they're quite dynamic. 10 seconds later, the network might look like this. So from the bidirectional symmetric, we have now asymmetric. From unidirectional, it's bidirectional. We have a separation into two networks. How should you do routing there? So, this is the problem in ad hoc networks. Very dynamic. The quality of the channels varies within a few seconds, sometimes milliseconds. So that's really a problem. Let's have a look at traditional routing algorithms. You know distance vector link state. So distance vector from computer network class, periodic exchange of messages with all neighbors, and then you will get information about who can be reached at what distance. You select the shortest path. You know how far it is from your neighbor to a certain destination. Then you add 1, for example, then you know the distance from your place to this destination. Then there are link state algorithms. Link state, the idea is all the routers want to get a complete picture of the network. So periodically you exchange your view of the world with your neighbors, and this helps you updating your own view of the world. That's the link state. So in fixed network, OSPF, that's a classical version, and distance vector, that's RIP, and well, it's path vector, BGP. So these are, well, members of this family. But here we are in wireless and mobile networks. And it's interesting to see that many years ago, the first packet radio networks from ARPA, they used distance vector routing, exchanging routing tables, including the link qualities every 7.5 seconds, and they updated their tables after reception of packets. And if there are problems, well, flood. Flooding is always a solution, but, well, there are some performance efficiency problems. So routing is a big problem because you have these really dynamic networks, maybe sometimes only unidirectional links. So you cannot simply use an OSPF or whatever protocol from fixed networks because they all assume bidirectional links and very stable links. Stable and bidirectional. And here we have everything. Bidirectional, unidirectional, not stable at all. That's a problem. So routing was over many years the big topic on ad hoc networks. There are so many proposals, hundreds of them, and there's always the most simplest one. And many of those schemes, they fall back to flooding. The classical approaches, they all fail. Overhead is way too large, very slow convergence. And the problem is the network changed. Before you converge to a shortest path to a solution, the network changed already. With only maybe very low computing power. These are not powerful routers, but some battery-driven devices, low bandwidth. Then what about the metrics? Is it number of hops, or is it loss rate? Or is it to maximize the battery runtime? Is it to stabilize the network? Or the time of connectivity of all participants of the network? So metrics for routing are completely different. This is not a simple hop count, or this is not a simple what is the load on a single link. Maybe it's a radio interference. Maybe you want to minimize the interference between nodes. So metrics are way more complex. So the problems of traditional routing algorithms are mainly, well, topology is too dynamic. Frequent changes of the connections, of the participants, coming up, going down, churn rates quite high, and we do not have high performance systems. So we cannot do this quite frequent periodic updates of the tables. So this really kills all sleep modes because our devices, they want to sleep most of the time. We have limited bandwidth, so you cannot simply exchange huge routing tables. And the asymmetric links, that means, okay, maybe I can send you something, but the way back doesn't work. So if you set up larger networks, we experienced up to 70% of the links are asymmetric and unidirectional. So that really is a big problem. I will show you one very simple example of a so-called reactive routing protocol, a classical routing protocol. It's called dynamic source routing, just to show you the basic idea and the basic problems. So the idea here in DSR, dynamic source routing, is you split the job of routing into how to discover a path and, if needed, how to maintain a path. This is a so-called reactive routing protocol because we discover a path only if we want to send something to a destination. Only if this is needed and there's no current path. In the internet, you will see there are paths available if you send something or not. And in DSR, we maintain a path only as long as the path is in use. And then you have to make sure that you can further on use it. Otherwise, no. There are no periodic updates. How does it work? Okay, first of all, path discovery. Very simple algorithm. So the first thing you do is you broadcast a packet with a destination address. Okay, that means at least everyone has an address. That's a complete different topic. How do you get your address, your unique address, etc. Let's assume everyone has an address and a unique ID. If you are a station somewhere in the network, well, first case, you are the receiver. Perfect. This means you have the correct destination address. Then you can return the packet to the sender using the path that we collect during setting up the path. I will show you how this works. But to be honest, that requires bidirectional links, as we will see. So you already see, okay, there's a problem, maybe. But first, let me explain it. Second possibility, you saw this packet already. It's broadcasted. Then discard it. And third possibility, that means never seen this packet before, but I'm also not the destination, then append your own address and broadcast it again. So that's the idea, and then the destination node will get a path and send this back the reverse way to the sender. There are some optimizations, so you can limit the broadcasting if you know the diameter, you can cache paths or part of the paths, things like this. So how does it work? Very simple. You want to send from C to O. Okay, all you can do is broadcast. Well, it's a wireless link, so you broadcast anyway. Wireless, it's an antenna. You always broadcast. But here we're operating on layer 3, but we use the broadcast from the physical layer, so it's a broadcast. So there's an identifier, 4711, and it tells, okay, I want to set up a path to O and I'm C. Then all the nodes will include, okay, I append my address and broadcast. So G will send it again to all the other nodes, as well as B appends B and broadcasts. You will see some of the packets will be broadcast back to C. Well, quite obvious. But you detect, oh, it's 4711, I know this one, drop it. That means now you will see like a kind of wave front. This packet will go through the network. Some nodes will drop it. There are sometimes some alternative routes. Well, this now depends on the medium access, who is the winner. But sooner or later, the packets will reach the destination. And in the destination now, you will find the path. CGIKM. And that's the idea. Okay, now that's the last time of broadcasting, but finally we have the path and can send it back if the links are bidirectional. If not, well, we have to do the same the other way around, but then we have the problem, then both sides have the path for the other side. So this really is something for bidirectional links. Okay, that's how we set up the path. And then we have to maintain the path. Okay, maintaining paths, that means after we send a packet, we wait for, now you see, layer 2 acknowledgement if applicable. Yeah, for example, wireless LANs, they have the layer 2 acknowledgement. If we hear the layer 2 acknowledgement from the other side, perfect. So at least we know they received it, or we can listen to the medium if this is symmetric to detect if the other station forward the packet. So it depends what works. Or we request an explicit acknowledgement. So, and if we encounter a problem, you can inform sender of a packet and look up a new path locally, or the sender has to look up a path. So maintenance depends on layer 2, how you really want to do this. But this is a typical reactive protocol, setting up a path as soon as you want to send something. This may take some time, but it does not waste any energy if you do not have to send anything. I told you there are many different metrics now possible. Just to give an example, interference-based routing. That means maybe the shortest paths from a sender to a receiver, shown here, these thick solid lines, they're not maybe the best ideas, because if you send simultaneously, we will create some interference here. So maybe it's better to pick these dotted line paths to avoid the interference. This is a metric you will never use in, let's say, a fiber optic network, something like this. But this is quite common for wireless networks, that you have to take care of interference. Complete different kind of metrics. And all these different metrics and considerations led to really many ad hoc routing protocols. There's the family of proactive and reactive routing protocols. I showed you DSR, one example, a prominent one from the reactive family. They are proactive, and proactive, that means they set up a path no matter if you need it or not. The big advantage then is as soon as you need the path, it's already there. And OLSR is a prominent member of this family. There are some hierarchical systems, there are some geographic position assisted routing protocols, so that you know where the receiver is by its geoposition, and many more. Quite prominent now is version 2 of OLSR, optimized link state routing. There's also an RFC for it. So that's proactive, exchanging tables, and this is an optimization of the classic link state routing like OSPF, for example. And the idea there is that you will not broadcast, like a classical link state routing, your table to everyone, but you select certain multi-point relays, and these are specialized nodes, well, that have the role of a multi-point relay, and with the help of these relays, you have to make sure that you can reach all 2-hop neighbors. So what is a 2-hop neighbor? If you're here somewhere, then this is a 1-hop neighbor, and then this is a 2-hop neighbor. And if you have a network like this, for example, so there are many more nodes, things like this, whatever, something like this, and then you have to make sure that you reach each 2-hop neighbor. 2-hop neighbor, 1, 2, or this one. You have to be able to reach these 2-hop neighbors. And with the help of such multi-point relays, you can make sure that if you use only these specialized nodes, you can reach these 2-hop neighbors. Then these specialized nodes are the ones to perform the flooding, and not everyone. So in link state, classical OSPF, all the routers perform flooding, so that does not really scale classical OSPF, but here we select special multi-point relays. If you're further interested in OLSR, please do have a look at many of these initiatives using this for setting up ad hoc networks using wireless LAN technologies in cities, independent networks, independent from any network operators. They quite often use OLSR. Okay, so that's a prominent member of the proactive routing. And then there are so many more issues you could talk about. How to do the address configuration. Where do I get my address from? How do I know my function as a node? How do I discover services, multicasting, quality of service? Oh my, that's already a problem in the fixed internet. Now we have ad hoc networks. If you have ad hoc setting of more and less important nodes, how do you support this? Power control, sleep modes, security. Well, denial of service is always a problem, but data integrity, then scalability. Do those algorithms really scale to tens of thousands of nodes? That's a problem, and one way for supporting scalability is hierarchy. So quite often you see clusters of nodes with so-called cluster heads, and then these are the more powerful machines, and they set up a mesh network on their own, the cluster heads, and they collect data from other nodes. So that's one way of handling these, well, scalability issues. Okay, that was kind of a first look into the problems of ad hoc networking. And now you should at least have a feeling why routing is quite difficult in ad hoc networks. Why is this the case? And which problems do traditional routing algorithms have in these wireless and ad hoc settings? Why can't we simply use them? You learned roughly the ideas of those two families, proactive, reactive routings. What is the difference? What are the advantages and what are the disadvantages? And then you learned something about new metrics for wireless ad hoc routing. That's quite different from the fixed networks. What are these new metrics?